The gas turbine cycle that has been presented here is the most simple gas turbine cycle, that is called the single shaft gas turbine, because the compressor, the turbine, and the machine that is run by the cycle are all placed on the same shaft or axis. It's one of the consequences of this is that we need to have the same rotation velocity for all these three devices when we have this kind of cycle. There are other gas turbine cycles for which we decide to have two different shafts, so they can be either concentric or at different locations. And for this one, usually we change what we have here. We have one first stage of turbine that is called the high pressure turbine, that is designed so that the technical work provided by this turbine equals exactly what is required for the compression of the fluid, so the technical work received by the compressor. So when this is done, then the fluid is only partially expanded in this first stage of turbine at high pressure, and so we have an intermediate pressure, like middle pressure, at the outlet of this turbine stage. So then the remaining pressure can be expanded in another stage of turbine, so that would be called the low pressure turbine stage, and so the smoke is sent for expansion in this other turbine stage, and so this is fully expanded until atmospheric pressure, and then we have the exhaust of smoke only at the outlet of this lower pressure turbine stage. Then the technical work that is provided by the fluids to this lower turbine stage can be used to run any machine. So for example, once again, a propeller, if we speak for example of turbo propeller for aeronautic propulsion. And one big advantage we have here is that we can have different rotation velocity for this second shaft. That's the one we have for this high pressure shaft. And indeed, because the size of the propeller for the propulsion of the airplane is much bigger than, for example, the compressor or the high pressure turbine, we need a lower rotation velocity on this second shaft. So this is possible if we do this kind of things. So now let's present something else that can be done with this partially expanded smoke, so this flow of smoke at intermediate pressure. So if we keep the same base, so a high pressure turbine stage that is used uniquely to provide the technical work required by the compressor, we can use this flow of intermediate pressure and expand it in a nozzle. So if we have, for example, a nozzle, and this gas is finally expanded in the nozzle, what we get at the outlet of the nozzle is a high velocity. Check. From a thermodynamic point of view, the enthalpy of the fluid has been converted into kinetic energy. That's exactly the principle of a turboreactor, to eject the smoke at a much higher velocity than the velocity of the air that is taken inside the turbo reactor, and then the reaction of the air to this high velocity jet causes the propulsion of the airplane by reaction. So that's something else we can do, and that's another kind of gas turbine. So now let's go back to what we had initially, with one single stage of expansion, so one single turbine with a full expansion, and let's look at other possibilities we may have for the gas turbine cycle. Until now we have been considering what we call internal combustion, so we were injecting fresh air into a combustion chamber, we were adding fuel inside the combustion chamber, then combustion was taking place within the working fluid that was converted into smoke, and this way it was possible to increase the temperature of the flow. The purpose of this device is the temperature increase. So we want to increase the temperature of the flow, and this is possible another way. Another way would be to have a heat exchanger and to have a heat exchange with another fluid on the other part of the heat exchanger. So if I draw this way a heat exchanger, then we have heat coming from a hot source, so QH, that is exchanged from the secondary fluid to the primary fluid. And one advantage we may find here is that we can have external combustion, so we can have other types of fuel that can be used if we do this this way. So if we do that, another advantage we have is that we don't have any change of the nature of the fluid that is going across this heat exchanger. So if we have ambient air at the inlet but cold air, we will have only hot air but the same chemical nature for the fluid at the outlet of the turbine. So because we have now the same nature of fluid, it is also possible to bring back this hot air into the initial state we had at the inlet of the compressor by just cooling it down, because both of them are at the same pressure. We can close this cycle by adding another heat exchanger. So then this second heat exchanger will exchange heat with, from a thermodynamic point of view, the cold source. So it will give, the working fluid will give heat QC with the cold source that will be at the other side of this heat exchanger, and it is like this possible to close the cycle. So of course this is only part of it, because there's a remaining torque on this shaft, so we don't forget here that we have a machine connected to this, and if we have heat exchangers and secondary fluid, then it becomes also a heavy machine, so it's not for propulsion of an airplane anymore, but this machine can be, for example, an alternator for electricity production. So now that we have this closed cycle, of course this kind of gas turbine cycle is not very frequent, but it's still possible to make. One advantage could be that another fluid than air can be used, so we can possibly use other gases to work as working fluid and to undergo this different transformation, and so we may find fluids that have better properties than air for this. But another big advantage is this kind of cycle is easier to model from a thermodynamic point of view. So in this chapter we will first take this closed gas turbine cycle with external combustion as base cycle that will be studied, and at the end we will look at the difference into the modeling we have when we have open cycles with internal combustion.